Welcome to a lesson with Dr. Powell. Let's take a look in this video at computing the derivative function of f of x equals x squared minus x plus 1 using the limit definition of a derivative. Okay, so we're going to use the A strategy. We have our 1 point because we're finding the slope of the tangent line at a point x. One of the points is going to have an x in it. So x, comma, and then what's the y value? Just plug it into the function, x squared minus x plus 1. And we're going to pick a point nearby. The x value, we'll just call it a. And then we have a squared minus a plus 1. We're going to compute the rise over run between these 2 points and take a limit as a approaches x. A is the variable of the limit, x is a constant. So we have the difference between the two y values is the rise, a squared minus a plus 1 minus quantity, x squared minus x plus 1. Now remember, put parentheses around the second, around this y value right here, so you can remember the negative will distribute through to each one of those terms inside, all over, and then just a minus x. So we're going to compute that limit. We cannot simply set a equals to x because that is out of the domain of this expression, remembering that a is the variable, x is the constant. So we need to maybe simplify the top in some way such that we'll see maybe a minus x is a factor of the top, so we'll get some cancellation and the domain will change. So let's think about that for a minute. All right. First of all, notice that we have a 1 here and then a minus 1. So the 1's will cancel. 1, and so this negative distributes through, right? And so this 1 and minus 1, which happens upon the distributing, so those will go away. So let's write down what we have so far. We have a squared minus a minus x squared plus x. All right. And all that is over a minus x. Now, actually, it's kind of convenient to realize that in our computation and calculation here, actually taking the derivative of this part, and this part can be done separately and added together. You can kind of see that because you see this a squared and x squared. We can like put them together, and like this a and x, we can put them together off the side. And really, where did those come from? This a squared and x squared only came from the x squared part. These guys only come from that part. And really, if we put them off the side, it's as if we just, and let's take it up here, we just did as follows. Limit a approaches x, a squared minus x squared over a minus x plus, and then I'll write negative a plus x over a minus x. What in the world did we just do? In fact, I can distribute the limit through across this addition. But wait a minute. But before I do that, what did we do? Do you see what we did? We just unadded the fraction. Same denominator, right? If you add this back together, what happens? A minus x is the same denominator. These guys are added together. And so let's just put the negative a in front of the negative x squared. Hey, it looks the same. It is equal. That's all we did. We just kind of did an unadd fraction step here, using the same denominator, just kind of putting in two places and putting some things together. So now, if we think of this as being something like this, like limit of this plus limit of that, realize, hey, this is what I'd get using the A strategy if I was just dealing with, A and, let's see, a squared and x squared. Notice, you can try it out. Rise over run would give you that. So this really computes the derivative function of just x squared. Okay, so this is the portion that computes the derivative of just x squared. What about this portion? Similarly, let's think about this. Actually, if I thought of the function negative x, let's think. One point would be a negative a, the other point would be x negative x. Try it out. See, what do we have? Rise, negative a plus x. Run, a minus x. Yeah, so this really computes the derivative function right at negative x. Notice how they kind of add. So you can kind of, if you have some things added together, you can take the derivative of this part plus the derivative of that part plus the derivative of that part. Now this doesn't work with multiplication and other things, just addition and subtraction. Okay, we cannot do this otherwise. But for derivatives, and we can see that kind of in how this limit is working. So really, if you see something like this, you could just split it up and do, hey, let's do this part. Hey, then let's do this part. Then let's do this part. Now wait a minute, the one kind of went away. Well, let's think about what's happening here. I mean, this really looks like 1 minus 1 over a minus x. That looks like I have like a point a1 and x1. So in other words, it's like the function, now this is of course y equals, and y equals 1. But what's the slope of a line y equals 1? That's a horizontal line. The slope is 0. Slope of the tangent line 0. Of course it's going to zero out. It's not going to matter. If I see constants added on, we can ignore them like this, as long as they're just like outside of everything. Not inside a square root, not inside a square, not inside anything, just kind of by itself, a lonesome, added on, then it'll go away. But otherwise, you might have to worry about it. So just keeping that in mind here, if that helps anyone with the computation. I'm doing a little bit of extra explanation, but hopefully it just helps. But really, we haven't really done anything yet. I just am jabbering away, but hopefully it helps us kind of think about strategy with how we want to do this. So we could have just started this problem by just saying, boo! We're even using a limit, just thinking about it, and just focusing on this part. This x squared part, let's just compute this limit. This negative x part, let's just compute this limit. So we got those two limits. Now let's go for it. The strategy is actually really nice here. So if we think about this, we could factor this right away. See that? A squared minus x squared. We can go a minus x, and then a plus x, and then we have a minus x. All right, domain changes immediately. We're taking a limit as a approaches x. We could just throw x in. Notice that this part we get 2x. So from this part, we just get simply a 2x. And we're going to add to that what we get from this part. All right, and this is an equal sign. Okay, so what do we get from this part? Notice if I factor a negative out of the top, and we're going to have a negative a, and then you have to put a negative x so that when it comes back in, you get a positive x. Double check it, negative a plus x, same thing. Now, why did we do that? So we can see some cancellation, so negative 1. So a minus x, quantity will cancel, and we're taking a limit, but it doesn't really matter because there's nothing to plug in for a because there's no a's anymore. It's just negative 1. So this is negative 1. All right, and of course you get 0 from there. So the derivative function in this case is simply f prime of x is equal to 2x minus 1. Thanks for watching.